Networking 101, Chapter 1 Speed is a Feature. The emergence and the fast growth of the web performance optimization WPO industry within the past few years is a telltale sign of the growing importance and demand for speed and faster user experiences by the users. And this is not simply a psychological need for speed in our ever-accelerating and connected world, but a requirement driven by empirical results, as measured with respect to the bottom-line performance of the many online businesses. Faster sites lead to better user engagement. Faster sites lead to better user retention. Faster sites lead to higher conversions. Simply put, speed is a feature. And to deliver it, we need to understand the many factors and fundamental limitations that are at play. In this chapter, we will focus on the two critical components that dictate the performance of all network traffic: latency and bandwidth. Figure 1:1. Latency: the time from the source sending a packet to the destination receiving it. Bandwidth: maximum throughput of a logical or physical communication path. Figure 1:1. Latency and bandwidth. Figure 1:1. Latency and bandwidth. Armed with a better understanding of how bandwidth and latency work together, we will then have the tools to dive deeper into the internals and performance characteristics of TCP, UDP, and all application protocols above them. Decreasing transatlantic latency with Hibernia Express. Latency is an important criteria for many high-frequency trading algorithms in the financial markets, where a small edge of a few milliseconds can translate to millions in loss or profit. In September 2015, Hibernia Networks launched a new fiber optic link, Hibernia Express, specifically designed to ensure the lowest latency between New York and London by following the Great Circle route between the cities. The total cost of the project is estimated to be $300 plus, and the new route boasts 58.95 ms latency between the cities, which gives it a 5 millisecond edge compared to all other existing transatlantic links. This translates to $60 plus per millisecond saved. Latency is expensive, literally and figuratively. The many components of latency. Latency is the time it takes for a message or a packet to travel from its point of origin to the point of destination. That is a simple and useful definition, but it often hides a lot of useful information. Every system contains multiple sources or components contributing to the overall time it takes for a message to be delivered, and it is important to understand what these components are and what dictates their performance. Let's take a closer look at some common contributing components for a typical router in the internet, which is responsible for relaying a message between the client and the server. Propagation delay: amount of time required for a message to travel from the sender to receiver, which is a function of distance over speed with which the signal propagates. Transmission delay: amount of time required to push all the PACKETS bits into the link, which is a function of the PACKETS length and data rate of the link. Processing delay: amount of time required to process the packet header, check for bit level errors, and determine the PACKETS destination. Queuing delay: amount of time the packet is waiting in the queue until it can be processed. The total latency between the client and the server is the sum of all the delays just listed. Propagation time is dictated by the distance and the medium through which the signal travels. As we will see, the propagation speed is usually within a small constant factor of the speed of light. On the other hand, transmission delay is dictated by the available data rate of the transmitting link and has nothing to do with the distance between the client and the server. As an example, let's assume we want to transmit a 10 MB file over two links, 1 Mbps and 100 Mbps. It will take 10 seconds to put the entire file on the wire over the 1 Mbps link, and only 0.1 seconds over the 100 Mbps link. Network data rates are typically measured in bits per second (bps), whereas data rates for non-network equipment are typically shown in bytes per second bps. This is a common source of confusion. Pay close attention to the units. For example, to put a 10 megabyte MB file on the wire over a 1 Mbps link, we will need 80 seconds. 10 MB is equal to 80 MB, because there are 8 bits for every byte. Next, once the packet arrives at the router must examine the packet header to determine the outgoing route, and may run other checks on the data. This takes time as well. Much of this logic is now often done in hardware, so the delays are very small, but they do exist. And finally, if the packets are arriving at a faster rate than the router is capable of processing, then the packets are queued inside an incoming buffer. The time data spent queued inside the buffer is, not surprisingly, known as queuing delay. Each packet traveling over the network will incur many instances of each of these delays. The farther the distance between the source and destination, the more time it will take to propagate. The more intermediate routers we encounter along the way, the higher the processing and transmission delays for each packet. Finally, the higher the load of traffic along the path, the higher the likelihood of our packet being queued and delayed inside one or more buffers. Buffer bloat in your local router. Buffer bloat is a term that was coined and popularized by Jim Geddes in 2010 and is a great example of queuing delay affecting the overall performance of the network. The underlying problem is that many routers are now shipping with large incoming buffers under the assumption that dropping packets should be avoided at all costs. However, this breaks TCP's congestion avoidance mechanisms, which we will cover in the next chapter, and introduces high and variable latency delays into the network. The good news is that the new Codel active queue management algorithm has been proposed to address this problem and is now implemented within the Linux 3.5 Plus kernels. To learn more, refer to controlling queue delay in ACMQ. Speed of light and propagation latency. As Einstein outlined in his theory of special relativity, the speed of light is the maximum speed at which all energy, matter, and information can travel. This observation places a hard limit and a governor in the propagation time of any network packet. The good news is the speed of light is high. 299,792,458 meters per second, or 186,282 miles per second. However, and there is always a however, that is the speed of light in a vacuum. Instead, our packets travel through a medium such as a copper wire or a fiber optic cable, which will slow down the signal table 1:1. This ratio of the speed of light and the speed with which the packet travels in a material is known as the refractive index of the material. The larger the value, the slower light travels in that medium. The typical refractive index value of an optical fiber through which most of our packets travel for long distance hops can vary between 1.4 to 1.6. Slowly but surely we are making improvements in the quality of the materials and are able to lower the refractive index. But to keep it simple, the rule of thumb is to assume that the speed of light in fiber is around 200 million meters per second, which corresponds to a refractive index of tilde 1.5. The remarkable part about this is that we are already within a small constant factor of the maximum speed. An amazing engineering achievement in its own right. Route distance time, light in vacuum time, light in fiber round trip time RTT, in fiber New York to San Francisco, 4,148 km, 14 ms 21, ms 42 ms New York, to London 5,585 km 19 ms, 28 ms 56 ms New York, to Sydney 15,993 km, 53 ms 80 ms, 160 ms equatorial circumference 40,075 km 133.7 ms, 200 ms 200 ms table 1:1. Signal latencies in vacuum and fiber. The speed of light is fast, but it nonetheless takes 160 milliseconds to make the round trip RTT from New York to Sydney. In fact, The numbers in Table 1 to 1 are also unrealistically optimistic, in that they assume that the packet travels over a fiber optic cable along the Great Circle Path, the shortest distance between 2 points on the globe, between the cities. In practice, that is rarely the case, and the packet would take a much longer route between New York and Sydney. Each hop along this route will introduce additional routing, processing queuing, and transmission delays. As a result, the actual RTT between New York and Sydney over our existing networks works out to be in the 200-300 millisecond range. All things considered, that still seems pretty fast, right? We are not accustomed to measuring our everyday encounters in milliseconds, but studies have shown that most of us will reliably report perceptible lag once a delay of over 200 milliseconds is introduced into the system. Once the 300 millisecond delay threshold is exceeded, the interaction is often reported as sluggish, and at the 1000 milliseconds 1 second barrier, many users have already performed a mental context switch while waiting for the response. See speed performance and human perception. The point is simple: to deliver the best experience and to keep our users engaged in the task at hand, we need our applications to respond within hundreds of milliseconds. That doesn't leave us, and especially the network, with much room for error. To succeed, network latency has to be carefully managed and be an explicit design criteria at all stages of development. Content Delivery Network (CDN) services provide many benefits, but chief among them is the simple observation that distributing the content around the globe and serving that content from a nearby location to the client enables us to significantly reduce the propagation time of all the data packets. We may not be able to make the packets travel faster, but we can reduce the distance by strategically positioning our servers closer to the users. Leveraging a CDN to serve your data can offer significant performance benefits. Last mile latency. Ironically, it is often the last few miles, not the crossing of oceans or continents, where significant latency is introduced. The infamous last mile problem. To connect your home or office to the internet, your local ISP needs to route the cables throughout the neighborhood, aggregate the signal, and forward it to a local routing node. In practice, depending on the type of connectivity, routing methodology, and deployed technology, these first few hops alone can take tens of milliseconds. According to the annual Measuring Broadband America reports conducted by the Federal Communications Commission (FCC), the last mile latencies for terrestrial-based broadband DSL, cable fiber, within the United States have remained relatively stable over time. Fiber has best average performance 10 to 20 ms, followed by cable 15 to 40 ms, and DSL 30 to 65 ms. In practice, this translates into 10 to 65 ms of latency just to the closest measuring node within the ISP's core network before the packet is even routed to its destination. The FCC report is focused on the United States, but last mile latency is a challenge for all internet providers, regardless of geography. For the curious, a simple traceroute can often tell you volumes about the topology and performance of your internet provider. Greater than traceroute google.com traceroute to google.com 74.100 25.224.100 264 hops max 52 byte packets 110.1.10.1 10.1.10.1 7.120 ms 8.925 ms 1.199 ms 296.157.100.196 .157.100.1 20.894 ms 32.138 ms 28.928 ms 3x.santaclara.xxxx.com 68.85.191.29 9.953 ms 11.359 ms 9.686 ms 4x.oakland.xxx.com 68.86 143.98, 24.013 is 21.423 is 19.595.